Welcome to another one of our Platinum sponsor fireside chats or get to know our sponsor sections. And this time we're talking to Subspace. Now, Subspace are kind of awesome to me for a number of reasons. And that's partially because of Broadcaster VC, and that's what we're using to record all of these sessions before the actual conference. And it helps power that. And I've been super excited about Subspace as a global turn network for a long time. Ever since me and William, you'll meet William in a minute. Ever since me and William talked about the idea of this a while back now, I've wanted to get involved and wanted to use the service. So when it became available a couple of months ago to me, I couldn't wait to get involved with it. And then I talked to them about ComCon and what we were doing with ComCon, and they were like, yes, let's get involved. So I'm going to hand you over to Alex, and he's going to talk about Subspace and what Subspace is, and so that you can get to know who they are. And then after that, I'll have a chat with William, and we'll go from there. So I'm just going to hand you over to Alex right now. Take it away, Alex.
Thanks, Dan, and thank you for that introduction. So, as we know, and it seems pretty timely, especially with what we've all been dealing with over the, past almost 2 years now with COVID and remote from work. What we've really sort of known always, but really I think got to experience it firsthand, is that the internet today wasn't built for real time. With all of us having to work remotely, whether it be from home or otherwise, we've sort of learned how that, voice, video applications and other real-time applications using our home internet connections, they work, but they don't work good enough, and they're not reliable, it's not stable, and it's not consistent. And so at Subspace, we were founded in 2018, and we set on a mission to really change this, to really redesign the internet by creating a speed of light parallel network to the internet that we know today, so that it not only supports and makes the experience better for real-time application use today, but is also going to build a platform in which next generation real-time applications will be able to be built on top of in the future. Applications that none of us have even ever dreamed would be possible. How we started was we started in the online multiplayer gaming industry, solving matchmaking problems for gamers. And if you think about what a gamer is, they are a real-time application user sitting at home, connecting to a set of infrastructure that might be close to them, might not be, depending on where in the world they are. And typically gamers, they want to game with other people on the other side of the world. Playing a game with your neighbor's fun, but playing a game with somebody who's halfway across the world is even better. And so what we were able to do is we were able to solve this latency issue for gamers halfway across the world, to the point where we were able to show improvement in latency of up to 80% improvement. And now, today, we have over 400 million users, data and traffic, I should say, going across our network. And it's shown us how the internet moves across the world, and we're able to actually weather map that traffic to gather telemetry and be able to route traffic accordingly to provide stable, better connections for users. So where does Subspace fit in the market? We often if we look historically, what organizations like Akamai did for storage and caching in the mid-90s really allowed e-commerce like Amazon, eBay to come to fruition. So if you remember back in the 90s, being able to opening up your web browser and going to a website, maybe an e-commerce website like eBay, images would take forever to load depending, again, where you were in the world. And so those images would later be stored and cached by organizations like Akamai and other CDNs to improve the load times of that content, that cacheable content. Then in the mid 2000s, AWS came in, and even Google Cloud Platform and the like, and they've really managed to make computing much more cost effective and allowed organizations to scale regardless of what size they were, without having to spin up their own infrastructure and build out their own data centers globally. This paved the way for organizations like Netflix and Salesforce and others to come to fruition. And since 2018 and moving into the future, we believe that we're positioned to do what Akamai did for storage and caching, what AWS is doing for infrastructure, Subspace is going to do for network, paving the way for cloud developers and developers of real-time applications to be able to build telemedicine applications, online multiplayer games, AR and VR applications, any application where time matters. So we've probably all experienced some of the work from anywhere challenges. Some of the biggest remote work challenges that organizations face are maintaining quality of service with remote workforce. So you can imagine larger organizations who've had branch locations in the hundreds have now gone over to the thousands, with everybody working from home, really essentially making each individual's home a new branch office. This has become a problem because now it's expanded the network edge for that organization. MPLS and SD-WAN deployments are really challenging when you're dealing with work from home, as it's very costly and in some cases not even possible to extend MPLS into someone's home. And there's still the inability to meet SLAs. If you look at a contact center or more specifically a business process outsourcer who has service level agreements with their customers, they still have to maintain those agreements even with agents working from home. And it's no longer a temporary thing. In the first 6 months of COVID, work from anywhere was really just being said to be a temporary thing. Oh, we'll all get back to the office. 76% of contact centers have said, we're going to let our agents work from home permanently. It's no longer a temporary thing. It's no longer we're going to get back to the norm. This is the new norm. So how does Subspace work its magic? Ultimately, we work our magic by weather mapping the internet. Just like Waze or Google Maps uses the user's mobile device to pinpoint the speed in which they're traveling and where they are, and gathers that telemetry in order to then make decisions about which path or which road or highway that individual should take based on the congestion of traffic. We do something very similar with Subspace. Traffic that goes over our network is able to move over the best paths. And one very unique thing about Subspace is we're able to actually change a session's path while it's in flight. So imagine there is two individuals, let's say a contact center agent, a live agent speaking with a customer. That customer maybe had to already wait 30 minutes in queue to get to that agent. They're frustrated. There's a conversation going, and all of a sudden, somewhere in between that agent and that customer, there's a fiber cut. Subspace is able to detect that, and in milliseconds can actually change the path of that session to a different path without interrupting or breaking down that tunnel. thus still maintaining that interaction and ensuring that that agent can fulfill that customer's inquiry and not have to go back into queue and redial. We do this through a combination of custom hardware and a fiber optic backbone, and of course, our software. In fact, our network is built comprised of about 80% software and 20% hardware. This is what our network looks like globally. We have over 110 POPs worldwide. Our goal is to deliver about 1,200 POPs worldwide because we ultimately want to be sub 5 milliseconds away from 95% of the global internet user. The closer we are to a user, the faster that user will come onto our network and the faster we can take their traffic to their destination. If you think of Subspace as a highway, more specifically as a toll highway, if you live closer to an on-ramp on a highway, that means that you're going to have less time between the time that you leave your house, get on the on-ramp, and onto the highway. And therefore, in theory, you're going to get to your destination faster. So our POPs are really the first point of presence in which a user's traffic is ingested into our network. And we also want to have POPs everywhere so that we're closer to the destination, so that traffic egresses out the closest POP to the destination server. Not only are we building a massive global network, we're also building it at lightning speed. About 2 months ago, we were ranked 16th most interconnected network in the world. Now, just recently, about 2 weeks ago, in fact, we have hit the top 10, surpassing Netflix with Amazon in our sights before the end of the year. This is an incredible feat. We're on our way to our mission of 1,200 POPs, making us the most interconnected network in the world. Let's take a look at our architecture. Very, very simple. We have designed this network so that there are no requirements for installation of hardware or software on either the client or the server end. It's all a network configuration. In fact, in most cases, the configuration to our network should take even a non-developer less than 30 minutes to configure. So, as I mentioned earlier, a user will connect to Subspace over their existing last mile provider. So we do not require the users to change their internet service provider. They can stay with their last mile provider, whoever that may be. And depending on what's the nearest Subspace POP, we actually GPS locate where that source IP is and will ingest that traffic because of our peering with local providers. We ingest that traffic in the nearest Subspace POP, carry that traffic throughout our network through the best path possible. And the best path is not always defined as the fastest. In many cases, it actually depends on the use cases. We have designed various profiles whereby, depending on the use case and application being that's leveraging Subspace, we can change profiles to be more balanced, where it takes consideration of latency, jitter, and packet loss more equally. Or we can even change a profile if it's a very, very latency sensitive application. We can heavily weigh our algorithm to latency so that even if a path isn't as stable or the most stable, if it's the fastest and that application needs the fastest, we will route the traffic through the fastest path. And then on the other end, again, we will egress the traffic from the closest Subspace POP to the server. So typically, if you're in the online gaming world, that'll be an actual game server, a contact center infrastructure, voice infrastructure, media server, what have you. We use Anycast Networking, and this is really nice because it makes configuration that much easier, especially when users or clients are globally dispersed. When Subspace provides an Anycast IP, the client any client, regardless of where they're connecting from, connects that same IP. So it's not a separate set of IPs depending on region. Again, making the configuration to Subspace that much easier. As I mentioned, there is no software or hardware required to use Subspace. It's all a network configuration. And in many cases, this could be done through a graphical user interface through our portal, which I'll be showing a little bit later, as well as an API configuration. We have 4 on-ramps with RTP speed over here on the right. This one is still in development, so I'll sort of leave that one separate for now. We have Packet Accelerator. This is sort of our main interface. It's our general TCP UDP interface. It will really look at 2 points and optimize the path between 2 points from anywhere to anywhere. So a great example is a remote desktop or a virtual desktop infrastructure where you have a client remote desktoping into a server or another endpoint. You give Subspace the external IP address of the destination. Subspace will provide an IP and port pair. The clients connect to the Subspace IP and port, and we pass the traffic over down to the destination. Very, very straightforward. SIP teleport. This is great for SIP-based applications, again, UC or contact center. The configuration is also very easy. You configure your SIP URI to your voice infrastructure. We then respond back with a Subspace IP and port. We support TCP, UDP, and over TLS as well. Clients will connect to the Subspace IP and port, which obviously can be done through DNS changes as well. And we optimize the RTP. Global turn. This is one of probably one of our most popular, especially of recent, is we actually are running turn in line within our network. So not only with Subspace are you getting an optimized network, but we've made it incredibly easy for WebRTC applications to on-ramp onto our network and have turn built in. So let's talk about a few case studies or use cases. We often find contact center. We looked at some of the longest paths in the world. Often organizations or other network companies are solving, intra-region really well. What we wanted to do is we wanted to actually run right into the hardest possible paths in the world and some of the longest paths in the world. Manila to Los Angeles is a great example. We have a customer who's got running virtual desktop infrastructure. They have agents in Manila, and in fact, many of them sitting at home with remote work now. And they're connecting to virtual desktop infrastructure sitting in a Los Angeles data center. The problem, well, this customer had MPLS, but the MPLS is not only expensive, but it's really redundant with people working from home. And so what we're able to do is these agents are able to use through using Packet Accelerator, are able to connect over Subspace to the infrastructure, providing a significant reduction in latency and therefore improving the virtual desktop experience, so that when they're on a call with a customer and they're pulling up a customer's account through their VDI application, the windows as they are clicking through the VDI infrastructure are actually happening quickly, and there are no delays, and therefore reducing call times and overall improving customer experience. So really quick, in this particular use case, unlike the medical industry, at Subspace, we like flat lines. Flat lines at Subspace is a great thing when we see them on a graph. In this case, we look at latency performance between Manila to Los Angeles. As you can see, the standard deviation as internet weather fluctuates, performance fluctuates. But with Subspace, we're able to keep that fluctuation at a minimum. And so in comparison to public internet with this example, we were able to provide a significantly reduced deviation, and therefore, and what that translates to is stability. Over 70% improvement in stability between Manila and Los Angeles versus public internet. And as far as speed and latency, just over 15%. So again, if you look at in reality using VDI, if an agent is on the phone with a customer and they've, you may often have experienced this yourself with the agent will sort of jokingly say, "Oh, I'm sorry, my computer's just a little slow today." Well, in many cases, it's not the computer, it's the network. It's the network causing latency, making it seem as if the local machine is actually running slow. And that just adds more delay, more time to that call. Customers have to wait longer, especially ones in queue. Overall quality of experience is down. But with Subspace, providing that stability, even with the agent working from home, it's almost as if they're in a delivery center with a private wide area network. Here's a quick look at packet loss as well. You can see in the blue, public internet, it's all over the place. With Subspace, it's a lot flatter, a lot more consistent. And again, standard deviation, much lower, with an improvement in stability, again, over 70%. And in fact, a performance improvement of over 69%. Another quick use case, contact center, using contact center infrastructure, voice infrastructure. We have a customer, Bangalore to Miami. And what they were having issues with is call quality. Call quality, again, quality is results to poor quality of experience. And in fact, sometimes if packet loss is significant enough, now you're talking about calls dropped. And calls dropped, especially in contact center, means not meeting SLAs. And for especially a business process outsourcer, that could also mean financial penalties from their customers. So let's take a look again. Almost flat line with Subspace, all over the place over public internet. Because again, the public internet was just not designed for real time. It's designed for volumetric traffic, and its job is just to get it from point A to point B with no prioritization or optimization. And this was in fact using our SIP teleport interface. And again, latency, not only more stable, but significantly reduced. So let's, what you just saw were static slides. Let's actually show you live some statistics. So I'll jump into our console. We're very excited. This week was actually a very important week for us here at Subspace. We have our official launch of our network, which means for those of you who signed up on our wait list for months now, number one, we thank you. We appreciate your patience, but everyone is going to get access to Subspace through our portal this Thursday, November 18th. So we're very excited. I'll actually show you a little bit of a demonstration and a sort of a sneak peek look of our portal. This is our packet accelerator interface. Setting it up is very, very easy. Again, this is all API accessible, but I'll just be showing you guys the GUI for today's demonstration. So as you can see here, I have a whole bunch of different packet accelerators created, and it's one-to-one. So in this case, I've got several virtual machines running in various regions on Google Cloud Platform. I'll mimic sort of a VDI remote desktop infrastructure with this demo. So let's see, the first one on our list is Sao Paulo. So as you can see here, Sao Paulo, I've got the actual external IP. So this is the external IP that GCP gave me. And I've got a Subspace IP. And this is what this interface looks like. So when I came in to configure this, I named my destination or my accelerator. I put in the external IP address of the virtual machine. I specified the port. And once I've done that, Subspace has responded back with a Subspace port and IP. And again, this is an Anycast IP. So we'll go to Sao Paulo here. I'll bring up remote desktop. And let's find Sao Paulo first, which is .53. And I'm going to connect first over public internet. All right. So let's take a look at the results here. Round trip latency, hovering 148. Saw 150 there for a second. We'll just call it 148. Obviously, this specific tool right now is showing obviously real-time RTT, but you could use other tools as well to capture sort of historical. So we'll put it down as 148. Go back in here. Close that up. And now we'll go over Subspace. And if I go over here now, as you can see, the Sao Paulo packet accelerator maps to this Anycast, Subspace Anycast IP. So I'm going to find .1.51. Somewhere here. There we go. Okay. 138 over Subspace. All right. Oh, 137, 136, but we'll say 138. We'll give public internet a little bit of an advantage. And we'll now go to Frankfurt. As you can see here again, I've got Frankfurt destination .55 over public internet. .112 milliseconds. And by the way, where I physically am located, I'm actually located just outside of Toronto, Ontario, Canada. So these distances, are pretty decent as far as the paths. So we'll go 113 for Frankfurt over public internet. And then we'll go to the Subspace IP over to Frankfurt. So 69. There we go. Okay. Just give it another second. All right, we'll call it 107. A few more here. Maybe we'll do this. And I believe next we're Mumbai. It's like traveling without getting on a plane. So 244. 213. Oh, do I not have this set up already? Okay. There we go. I missed it that first time. Too many IPs. Bring that over. Okay, now this is over public internet to Mumbai from Toronto. Let's call it 269. And then we'll go over Subspace 97. Okay, we're at 242, 241, 240. All right, we'll call it 240. And then finally, we're going to go to Montreal. This is normally when I would try saying something in French, but I will save everybody that. 226. Alrighty, we're at 20 milliseconds over public internet to Montreal. The short distance ones are very interesting to see. Obviously, the long distance ones, everybody thinks they're obviously for obvious reasons, they're always interesting to see the difference. But the short distance ones are interesting as well because you look at, well, how much quicker can you go at with a short distance, and so we're gonna find out. Oh, 18 should drop down. I think I saw 17. Obviously, over time, things will just only get better as we continue to further optimize. So we'll call it 18. Alrighty. So let's take a look at our results. I'll just make this a little bit bigger here. So as you can see across the board, Subspace has provided faster latency than the public internet. Now, this obviously was a simple demonstration just showing latency, but very important metrics we feel, especially around stability, are jitter and packet loss. And it's not just about whether, regardless across the board around all metrics, it really isn't just about getting a low number for that particular time. It's maintaining a consistent number and performance over a period of time, and in particular, a longer period of time. And that's really something that's very key. And it's a nuance that we actually really take pride of and put a lot of focus into, because when we think about experiences, real-time experiences in many cases aren't just instant. They don't just happen for a minute or two. They usually are happening for a decent amount of time. If you think about a meeting, a corporate meeting, you're looking at 30 minutes, 1 hour. If you look at an interaction between an agent and a customer, obviously the interaction, the call lengths want to be short, but at the same time, most cases, personally, I would much prefer to have a good interaction through the entire interaction versus a great interaction for the first 10 seconds, and then it's just up and down, up and down, up and down. And so we strive to provide consistency, stability, in addition to low latency. That's a wrap for me. I really appreciate it. If anybody is interested in trying out Subspace, please go to www.subspace.com. You'll find our countdown ticker. Tweet us. Sign up on the wait list. Again, our launch is just around the corner. Back to you, Dan.
Thank you. Sorry, I thought I had my mic muted for a sec. Well, hopefully by the time that people are watching this, you would have already launched completely and been able to get started. I'm looking forward to that, seeing more people use Subspace for different applications. So I'm going to bring William in briefly because we're about at the 30-minute mark, but we'll have a bit of a chat, and then we'll move over to Q&A and let people ask questions in Matrix anyway. So hello, William.
Hey, how's it going?
I'm good. How are you?
Great. Having fun.
Good. I need one of those hoodies at some point.
That might be arrangeable, but we'll see.
So I mentioned this earlier. Broadcaster uses Subspace as its default turn network, and a lot of people, when you talk about turn especially with WebRTC, like obviously Subspace has the other stuff as well, like the SIP and the packet accelerator and everything. But for me, the WebRTC portion is hugely forefront, right? So a lot of people tell me, oh, you don't want to send your media over a turn network because that's just ridiculous. And I would agree with them up until a point, right? So, like, if you're just having a normal one-to-one conversation, a peer-to-peer conversation with someone in the same country, and it's not necessarily vital if you lose some packets, then sure, I completely agree. But Broadcaster is designed so that we can get broadcast quality media into AV audio desk, AV video desks, etc. And so packet loss and jitter and round trip time are hugely important, and that's why Subspace are our default turn network. So I guess I don't want to step on your talk too much, but what are the challenges? What's taken you so long to be able to get to this point that you feel comfortable launching? And I guess what can we see coming soon that you haven't talked about already?
Sounds fun. So one, a lot of people are saying, yeah, peer-to-peer, if you live in the same city, same metro area, same country, that, yeah, latency should be fine. Subspace, when we started measuring the internet about 3.5 years ago, we started realizing that there's a lot of use cases. I talk about Singapore a bunch, but basically every city, major metro, if you've got somebody on one ISP and then somebody on the other ISP living in the exact same metro, you'd be like, oh yeah, 20 milliseconds, 30 milliseconds. No, we're seeing normal cases of it being well over 100 because those two ISPs probably don't interconnect in that same metro. They probably, one of them did a router change, and now your audio going, same city, less than a few hundred kilometers away, is now going an extra 2,000 kilometers just because that's how the internet decided to route it. So on my talk, I'll go into a little bit more detail. I'm actually going to take the exact demos that Alex V just did and go at a much lower level. How does the internet actually work? And kind of show what some of the complexities are. It is crazy how little information that routers and the internet have to try and get packets from one place to another. And technically, if they get there at all, the internet works. And that's the best effort. And Subspace is like, best effort isn't good enough. I want something that is able to be basically speed of light over fiber or near that should be the latency between people. And what I like to do is say, hey, for every 100 kilometers between two participants, there should be about 1 millisecond of round trip time. And that's our goal. And in order to get that, that's actually where it comes down to the math of 1,200 points of presence globally, because without that level of granularity, you just can't get the network to the level that you need it. You use the description of like, it's common knowledge. You don't just send it through turn unless you have to. Well, Subspace is actually saying, you know what? That the reason why is that hairpinning effect. If you've got a turn server in Frankfurt, doesn't matter where you are or where the person you're talking to, all your media is going through Frankfurt. You can kind of control it that way. Subspace is, with our big network, is basically saying, you know what? I can find a server in between geographically, usually geographically in between the two participants. And that's where they'll land for turn. And so there's a much shorter path the audio and media will take. And we look at it and say, not only is it a shorter path, so the intuition of the less time the packets are on the internet, the better chance they have of actually getting to the destination. Well, yeah, that's true. That's true. But we actually measure it. So we're actually measuring to see, all right, is there some kind of internet weather on those paths? If so, we move it to the other ones so that you can enjoy yourself.
And you can do that in real time as well, can't you?
Yeah, we're able to do it. So because we're doing it with Anycast and BGP, one of the core pieces of technology that Subspace solved and patented was we had the ability to change the network path without interrupting the connection, but we can move geographically in between pops. We can force it over different other paths. And most engineers will say, wait a second, that's a massive complexity. Yeah, it actually is. But we can basically control every IP and port combination for the session and steer it through the graph of the different paths. And so as fast as our network is able to identify the better paths, the network can respond even quicker to get it to the right places.
And I did a mini interview with Subspace when Broadcaster announced that it was doing Subspace as a default turn network. And I remember saying during that, well, it's enabled broadcast to not need so many points of contact throughout the world, which is inherently more cost for us and more maintenance and absolutely everything that comes with that. But it means that if we force all of our traffic over turn, then and especially over Subspace, then that means that we don't need to run all those servers, because essentially you're acting as those servers for us. As long as you can get that media back to, say, London or San Francisco or Toronto, wherever we end up with our key points of contact, let's say, as long as you can do that extremely quickly, it means that I don't have to as a platform, which is hugely powerful, right?
Yep, absolutely. Yeah, the way I think about it so Subspace is basically saying there are a lot of use cases that have a latency envelope, which is kind of like, all right, this use case works really well if everyone's under 100 milliseconds. Or whatever their latency is, as long as it stays stable, there's a variation. So jitter is often referred to in telecom. But that latency envelope, Subspace is able to say, all right, if you've got a server in one spot and the default internet connectivity has so many kilometers, Subspace is increasing that radius of the number or the amount of users who can actually connect within that same latency envelope. And so basically we're drawing the much bigger circles for the exact same server. And as soon as you do that, you start realizing you can start hitting large populations because of the way the area of a circle increases with that radius. And so it's incredible. It's an outsized effect, that performance benefit that we give.
So it's important to say, well, it's not just the global turn network. There's also the SIP, SIP. What is it? The SIP
teleport, and packet accelerator.
Thank you, and the packet accelerator, and then later on you've got the RTP stuff coming as well, RTP speed as well. So I'm going to tell everyone you should definitely watch William's deep dive. I've labeled it as a deep dive. William's deep dive on how Subspace kind of works and all of that jazz, because it's such an interesting topic, right? And not many people are actually willing to talk about the in-depth stuff. So William's willing to do that, so that's great. So you should definitely watch his session. So I'm going to say thank you very much to Alex and William, and we're going to round off now, and we shall see you all on the next session. Hello, everyone. What a great session. I know it's a little bit longer than normal, but we kind of got into talking, and I didn't want to stop the flow. So yeah, we've got William's session tomorrow, where he'll go into more of a deep dive about the actual details about how Subspace works. I noticed there was unfortunately, neither William or Alex are here at the moment. So I'm going to field a question for them. So one of the questions in Matrix was, where is it? Do you guys have a demo with SIP and RTP? And I can answer this one for them. Just go and sign up for a Subspace account. They don't have a waiting list anymore, and then you can set up a SIP teleport. And when you set it up, you give it some details about like where the destination is, i.e. your server. And then they give you a fresh IP address, and you can send TLS over it, etc. If you want to. And then they rewrite stuff. The way it works is they automatically assign a packet accelerator to that SIP teleport, and so they're able to forward everything dynamically, and they rewrite the SDP and stuff on the fly. I think that's how it works. I'm sure Subspace will tell me if I'm wrong. So you should just be able to sign up and go try it, is what the answer should be, as far as I'm concerned. So yes, that's it for our fireside chat with Subspace. We'll be back in a minute with another video. And yes, if you're on YouTube, if you're watching this on YouTube, make sure you subscribe. And good day. Thank you very much.